All right, here we go. So I love this lesson because we are going to review all of Unit 2 and Unit 3 just with e to the x. Okay? It's a good, pause. Hey, do you remember everything from Unit 2? Do you remember everything from Unit 3? And if you do, you can handle this. If you don't, it's a good way to okay, I got to relearn this. I got to remember my rules. I got to do this. So it's a perfect lesson for right now. Next class, we are going to review Unit 2 and Unit 3 with log x. Okay? So derivative rules, function analysis with these two complicated functions, starting with e to the x. E is just like pi. It's just a number that occurs naturally in mathematics. Pi is 3.141592655. E is 2.718828, and then I don't know the rest of the numbers, but it doesn't repeat. It's a number that naturally occurs. Pi, you take the circumference of a circle divided by the diameter. That's a D. And you magically get 3.1415, et cetera, et cetera. E, you plug in larger and larger values into this expression, and you get 2.71828, blah, 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 blah. Okay? You might have noticed something similar to this if you ever talked about finance and compounding interest. It's like annual interest, X would be 1. If we talk about semi-annual compounding, this would be 2. You go to continuous compounding, all of a sudden E shows up. And that's when X is infinity. Notice X is in the exponent. Well, E likes to show up in the base of X to the exponent. E to the X is a naturally occurring function in mathematics. And we've looked at e to the x before. In Unit 1, we talked about how it is a very fast-growing function in one direction, and it's a no-growth function in the other direction. One thing we didn't talk about or specify that it's always positive. But it looks like that. And then its inverse is the log function. They're arch enemies of each other. They will fight each other to the death, and neither will survive. So log x looks like this. It is, if we remember from Unit 1, a exponentially slow-growing function. It will grow, but it will grow slower than any other function out there. What's important is that logs and e's undo each other. This is important for this unit and future units. If you, say, have e to the x, and you want e to go away, and you just want to get x, you would tell log to go fight e. And log and e would go fight each other. They both lose. X would survive. It's not an exponent x. It's just x survives. The log of e to the x is just x. So if I ask you, what's the log of e to the 4th? What would you say? And what about the log of e? Ooh, that's a good question. What is the log of e? The answer is 1, because e does have an exponent. So yeah, they fight to the death, and they leave the 1 there. Now, it goes the other way around. If you have a log, and you want to get rid of the log, you ask e to fight the log. E to the power, though, is what you do. That's a little caret symbol, just so I know that it's not multiplying. It's like underneath the log. And e to the log will fight each other to the death the other way and give you x. So e to the log 4 is just 4. Just like log e to the 4th. Okay? It's really important. Like, a lot of people are very intimidated by e to the x and log x, but I don't know, it's just like a square root for a square. You know, it's just like square roots will get rid of squares. Squares will get rid of square roots. It's like that with e's and log. Log will get rid of e. E will get rid of log. Yeah, that's it. Okay? All right. But now we're going to focus on e to the x, and we are going to look at its derivative. We'll start out with its derivative, but I'm going to remind you, do you remember how to sketch graphs of derivatives? Like, let's pretend you don't know the equation here, but you have a graph of f. Could you sketch its slope graph, its f prime graph? What we did was like think about tangents and think about the slopes, whether they were positive, negative, or zero. See if you can sketch the graph of f prime. This is unit 2 review. And we got negatives, less negatives, zero, positives, more positives. Hopefully you're seeing something that ends up looking like this. Well, we do now know there are derivative rules that you know the specific equation of this is 2x. Okay, so remember, plug in x's, get n's. That's what a derivative equation is. It's a tangent slope generator. It's an M generator. Remember, plug in x's into f of x, you get y. Okay. Let's do it for e to the x. Now, just a reminder, and you guys are starting off very strong, so thank you. Lessons are not designed to be copied down. Lessons are not designed so that you turn your brain off and you just kind of follow along. We are active during our lessons. We are actively participating. We are trying and we are failing. You have a quiz on Friday. We don't have a weekend, finally, in between classes. You have a quiz on Friday. Let's start right now, like being active, and make sure you're trying. I ask you to try so that you don't have to try as hard on your homework or you don't have to relearn everything, okay? So please, that's my expectation for you during lessons. Here's y equals e to the x. What does its slope graph look like? You don't know, so give it a shot. Good idea. All right, so we got slopes that are close to 0. So I got slopes that are close to 0. I have more and more positive slopes, so it looks like my slopes just get more and more positive. Well, the but is in this observation. For every single, and this is where Desmos is great, function, the slope or the derivative graph was always different. Like x squared, you sketch the blue line, that's 2x, that's the slope graph, right? You guys already sketched that. X cubed slopes are x squared. You looked at sine slopes, and they were cosine. You see that? You looked at anything. I can't even think of a different type of function. Like any crazy polynomial, x to the 4th plus 5x cubed. Its slopes are different, okay? And then we get to e to the x. And it's like, well, where the heck are the slopes? Well, they're right there. Now, the but is, this is new. This is a function, and this is where math works in mysterious ways. And like sometimes it's appreciated, but if it's not, whatever, just go with it. The derivative equation for e to the x is e to the x. The equation of this graph is e to the x. Now, this really confuses a lot of students, but we'll work our way through it and it's going to be okay. You plug in x's into this equation, you get m's, right? You plug x's into this equation, you get y. Well, they're the same equation. So that means the y's of e to the x are actually the m's of e to the x. It's like the same point gives you two pieces of information. Doesn't happen anywhere else. And that blows your mind. Don't worry about it. We'll work on it. Okay? This is different. When we take derivatives, usually stuff changes. When you take the derivative of x squared, you're like, oh, I get 2x. When you take the derivative of e to the x, you get e to the x. Now I did something there. I took the derivative. I have two different equations. This is a y equation. This is a y prime equation. They just happen to be the same. That's not double prime. That's just y prime. Well, it is y double prime, but okay. Okay, cool. Now, if I ask you to write an equation of a tangent line to e to the x at a half, this is a reminder. Hey, when was the last time you wrote an equation of a tangent line? What do you need? What's the general form of an equation of a tangent line? Start with that. Tell your neighbors. What do we need? Yeah, good. So we're starting with oh, yeah. Okay. Now, it's been a while, so if we forgot, it's okay. We know x is given to us. Now, we know y's come from y equals equations, and m's come from y prime equations. So, could you tell me what would go here and what would go here if we're talking about e to the x, y equals e to the x at a half? Tell your neighbors. No, we're not looking at 4 to the x right now. Don't look at 4 to the x. I'm just looking at e to the x. I want its y coordinate and its slope at a half. What? No. The plug in x and get the x. So the y.
You were doing so good.
Okay, so again, don't overthink it. If you want to take the derivative, go ahead. The derivative is e to the x, which means you plug 1/2 into here, you get e to the 1/2. Okay, that's the root of e. If you want to write it as root e, great. If you want to write it as e to the 1/2, it's great. That's your y coordinate you get from your y equation. Well, your tangent slope comes from your slope equation. You plug 1/2 in here, oh, you get the same thing. Yeah, so that's what kind of is confusing to students is usually the slopes and the y's are not the same. Well, they are for y equals e to the x. No, it won't. That's kind of the most confusing part of e to the x. Because after I change one little thing, sure. After I change one little thing, though, it won't be the same. So it's that's kind of the confusing part that we say, okay, let's move on. Because if I change the number, let's say I change it not from e to the x, but to 4 to the x. Well, 4 to the x's slopes are different than 4 to the x's equation. If I look at 4 to the x, the slopes are different from the function, okay? If I look at e to the anything else besides just x, if I look at e to the x squared, I notice the slopes very much are different than e to the x. If I look at x times e to the x, the slopes are different. And that's good. That's kind of what we're used to. It's only e to the x, just e to the x, where the slopes and the y's are different. So for all the other kind of different types of e to the x that are going to show up to you, that you're going to see, things are going to be different. Okay? And that's good. Cool. So if it's 4 to the x, I'll tell you specifically, the slopes are 4 to the x times the natural log of 4. Why? Don't ask. Honestly, I don't even know. It's just we need a little bit more. Now notice, we don't use the power rule. We don't bring this x down and subtract 1. We don't bring this x down and subtract 1. It's literally something else. It's its new rule. If this is any number, the derivative is that number to the x times the natural log of the number. This actually works with e to the x. Watch. And some people like to put this down because they like when things change when you take the derivative. I could write the derivative of e to the x as e to the x times the natural log of e. Is that any different than what I put down over here? Yes, no? Maybe so. No is the answer because the natural log of e is just 1, so that just goes away. So that means e to the x log e is really the same as e to the x, so we don't need it. Great question. We'll see that a little bit later. Okay? Okay. So 4 to the x. Its derivative is not 4 to the x. Its derivative is 4 to the x times the natural log of 4. Please write an equation for a line tangent to 4 to the x at a half. And then we have lunch. No, we got 10 more minutes. Great, we're in good shape. Don't forget that your derivative equation is an M generator. It's not M, it generates M's. You got to plug in X's into your slope equation to get M's. Good. No. And that's something else that shows up sometimes in this lesson. We are going to get answers that are not nice and we can't simplify, but we're just going to have to embrace and leave. Close. For this one, the y and the m are different. So we shouldn't get the same y and the m. That's the m. Good. So that goes right there. But we're done with the craziness with the m's and the y's always being the same with e to the x. That's the m. What's the y? Where do we get y from? The original equation. Okay. Plug in the half. What do you get? There you go. Cool. So, remember, plug in x's, get y's. Plug in x's, get m's. If I plug in a half into 4 to the x, I get 2. Oops, that's a y minus 2. If I plug in a half into 4 to the x log 4, I get 2 log 4. And that's like, we're kind of done with the tricky stuff where like m's and y's are the same. For all the other ones we're going to do today, the m's and the y's aren't going to be the same. So like, we got to take the derivative. We got to plug in x. We'll get an m. Boom. It'll be different. It's kind of back to normal. Okay. Now, if anything else shows up, whether it's in the power of e, or it's being multiplied by e, or it's being divided by e, we just are going to use our derivative rule. It's not going to be the same thing. f prime is not x squared e to the x. Like, no, it's not right. Okay? So, we are going to remember from Unit 2 our derivative rules. Because our derivative rules will help us when we have products of x's times x's. We can use the product rule. Okay, so remind yourself of the product rule. Tell me, what is f prime for this guy on the left? Go ahead. And then plug in 3.
No, I'm actually right. No, you're not. Is it 2x plus 3?
What?
Oh, wait, I didn't.
Okay. Thanks. Flip to the first and second plus. Flip to the second. This is where it's tricky. What is the derivative of e to the x? It's not just x. It's e to the x. The derivative of e to the x is e to the x. Okay? Okay. So here's where confusions happen. Either we forget the product rule, that's a problem. The derivative of the first times the second plus. Here's where the other confusion happens. Like, what's the derivative of e to the x? It's e to the x. Like, it's the one time where nothing changes, but you still did something. This is the derivative of e to the x. Okay? Like, I took the derivative, and it's e to the x. So, derivative first times the second plus the derivative of the second times the first. Second, plugging in 3. 2 times 3, 6 e cubed. E cubed times 9. I'd expect you to be able to simplify this. 6 e cubed plus 9 e cubed. What is it? 15 e cubed. Okay. And then interpret this without using the word derivative and without using the word slope of a tangent. Please interpret the meaning of this without using the word derivative or slope of a tangent. Go.
When x is equal to 3, there is 15 times e to the 3. Wait, m and y.
No, it's not true. The y is not the same. You get 9 e cubed. For the other one, yeah, we're not there yet. I'm back over here. I'm not there yet. What's the interpretation? Yes, at x equals 3, this is very important to remember, like, what do we find here? It's true meaning. At x equals 3. F of x is what? Why do you know it's increasing? Because it's positive. That's such a crucial thing in this class, that slopes being positive means functions are increasing. At x equals 3, f of x is increasing 15 e cubed y's per x. That means it's increasing really quickly. It's going up very, very quickly. Okay, great. Do you remember the quotient rule? Go ahead and rock the quotient rule.
So the derivative of the top times the bottom, and then the derivative minus the derivative of the bottom. What times the top divided by the bottom.
It is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, not the derivative of the bottom squared.
I take the derivative of the first, and then minus
See, we're remembering stuff. It's not that bad. Now, don't tell me that 2e squared minus e squared is 2. 2e squared minus 1e squared is 1e squared. 1e squared over 4. At x equals 2, that function is increasing e squared over 4y per x. All right, go to lunch. So we remember the product rule and the quotient rule, good. We remember the interpretation, good. Let's remember the chain rule. Didn't use the chain rule much last unit, but it's still there, and the chain rule is used a lot with e to the x. Tell me what the derivative of sine of x cubed is at 2. Go. You remember the chain rule. There's no e, that's an at symbol. This is just at. Do you remember the chain rule?
Is that right?
No. So this is why we do this. You know, we got to remember this stuff. You know, I appreciate the effort, and if we get it wrong, it's okay. Nice, well, yeah, you're done. Yeah, that's it. Yes. All right. All right, so kind of what we learned is if you see parentheses, you see a composition, not a product sometimes. This is not a product. It's a composition of an outside function and an inside function. You take the derivative of the outside and the inside separately. You multiply those together. You can multiply things in any order. You can put the 3x squared in front of the cosine parentheses. And what's the special thing about the parentheses? What starts in the parentheses stays in the parentheses. Don't change it. That's not a 3x squared inside the parentheses. It's x cubed. Then when we plug in 2, we should be getting 12 cosine of 8. And it's like, well, what's the cosine of 8? We don't know. So we just leave it like that, and that's okay. Okay? Okay. So that is a possible value, but like, no, because usually like our ratios are not involving pi. Like what's the cosine of like pi over 6? It's not pi over 2, you know, the cosine of pi over 6 is root 3 over 2. So it's like, it's something between -1 and 1. I don't know. Okay. Now we get to e to the x cubed. Okay. And we see this, and a lot of people are like, oh, let's bring this down and subtract 1, or let's take the derivative of x, blah, blah, blah. And the answers are no, 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 those are all wrong. This is a chain. You just don't see it. There are parentheses here. You just don't see them. This is an O and an I. You just don't see it yet. So let me help you see it. Ready? Here are the parentheses. There are the parentheses right there. This is a composition. We have an O and the I. Inside the parentheses is the x cubed. Outside the parentheses is the e to the parentheses. Just like we do with sign, sign parentheses, I'm going to write e parentheses. Okay? Okay, now. Nope. What do you think the derivative of e to the parentheses is? No. I said no. Newell's, right? Yep. 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 The derivative of e to the parentheses is e to the parentheses. The derivative of x cubed is 3x squared. So the derivative is, just like with sine, what starts in the parentheses stays in the parentheses. So this should be 3x squared times e to the x cubed. We do not put 3x squared into the power of e. It's a product. It's a chain. It's an O and an I. Which means the derivative, very similar to what we just had, is 12 e to the 8th, and that's okay. That's our answer. Now that we know what to do with e to a power where the power is different than x, let's look at e to the x over 3. E to the power and x over 3. Now, this brings us to something that we'll talk about a little bit more. E to the parentheses derivative is e to the parentheses good. What's the derivative of x over 3? Tell your neighbors. A lot of you will be wrong or confused, and it's not that bad. Yes. No. No. So x over 3 can be written as 1/3 x. Maybe that helps you realize that it's just.
If it was 1 over x to the third.
Then you would move it up. You're exactly right. All right, so the derivative of x over 3 is just 1/3. A lot of people make mistakes on that. So the derivative is 1/3 e to the x over 3. Okay, but notice I asked you to plug in something very unique. But you'll find that I chose that for a reason, because it simplifies nicely. The answer, after plugging in 3 log 4, is 4/3. The answer you get after plugging in 3 log 4 is 4/3. So you get e to the 3 log 4 over 3. The 3's go away. You get 1/3 e to the log 4. Now, this is very important. A lot of you will think that this is a fourth power and it's 1/3 to the fourth. Yeah, sure. E in log, fight to the death, leave the number 4, not the fourth power. So e to the log 4 leaves us with a 4, so the answer is 4/3. Now, go back a page because we had some space. Let's just make sure we don't make silly mistakes on some simple derivatives. If y is 5 e to the x, what is y prime? Write that down. What is 5 e to the x's derivative? What is 5 e to the x's derivative? You're right. I'm adding it on the previous page because I just want to make sure we get it.
I know it. Yeah, right? No, the 5 is outside.
Okay, ready?
I don't think.
Here's the easiest way I can help remember and remind you guys of this. What is 5 sine x's derivative?
5 cosine.
Okay, so you left the 5 and you took the derivative of the sine. Because it's not x's times x's, you didn't use the product rule. You just left the coefficients and you took the derivative of sine. 5 e to the x's derivative is 5 times the derivative of e to the x, which is e to the x, okay? So like, yeah, this is another example of like the y's and the m's are the same, but like coefficients, constants really trip students up. You shouldn't have your phone on you during the lesson. Okay. So I'm going to throw 12 next to e to the negative x. And I don't want you to get confused by it. Take the derivative of 12 e to the negative x. Put a 12 over here.
Oh, okay.
Yep. You just throw it in there at the end or keep it in there at the beginning. Yep.
Yeah, Ellen.
What happened to Ellen?
I think you're right.
No. You
Close.
can't.
Okay. So you got to notice that in the power of e, it's not just x, it's negative x. So you do need an O and an I. If it was just x, we don't have to worry about it. So I probably confused you with the last example. That means the outside, I'll include the 12 in the parentheses, and the inside is the negative x, whatever is in the parentheses. The derivative of 12 e to the parentheses, just like the derivative of 5 e to the x is 5 e to the x. The derivative of 12 e to the parentheses is 12 e to the parentheses. The derivative of negative x is negative 1, which means my derivative is negative 12 e to the negative x. Okay. Now we get to this one. It's the beginning of the combination of multiple rules. And a lot of people Thanks, Mitch. A lot of people will not see that combination. We see the 12e to the negative x, we see the sine x. The first thing you should notice is that you have x's times x's. The second thing you should notice is that the derivative of 12e to the negative x is negative 12e to the negative x. You already did it. So go ahead and write down the derivative of 12e to the negative x, sine x, and plug in 0. If you get it right, if you get it wrong, who cares? We're practicing. Make your mistakes now. What we want to do is make our mistakes now.
No, I know, but
Product rule. Product rule. You're right. Awesome phone. Answer's 12. Cosine of 0 is 1. Sine of 0 is 0.
What do you want us to call it? Like asshole or like what?
What?
Like Rocky Sanders.
No.
Baby carrot? I like that. Baby Johnson? Baby carrot.
We're good. All right. More stuff to review. Derivatives of derivatives with the chain rule. The answer is 12, sorry. So this is the derivative, negative 12e to the negative x sine x plus cos x times 12e to the negative x. We already took the derivative of 12e to the negative x, so we know what it was. If you wanted to, you would have to use an O and I. This was like coming out of the blue. And then the sine of 0 is 0, so this whole thing is 0. The cosine of 0 is 1. E to the 0 is 1. So that's how I just get 12.
Mr. Messer?
Yep.
What if you put the negative back here? Like 12e over. So it would be 12e over. 12 over.
It would be 12 over e to the x.
Oh.
And then e to the 0 is still just 1, so it should be 12. Okay, moving on. What if you put an 8? Please put an 8 in front of e to the x over 4. There's an 8, just remembering constants, don't worry about it. Please take the second derivative of g and plug in 4. Let's see if you can get this answer. This answer is e over 2. E over 2 is the answer. You can get that. 1/2 e is the same.
I did it before you said put in the 8.
And you got 1/18. That's correct.
Oh, okay.
and then you lose this guy out of class. Like this. The outside. Still 1/4, and then we'll plug in 4. I got it right away.
All right. So every time we take the derivative of e to the x over 4, we realize we need the derivative of the inside, which is a 1/4, which means the 8 gets multiplied by 1/4 twice. It turns into a 2, and then it turns into a 1/2. Plugging in 4, 1/2 e to the first e over 2. Cool. We feel good about ourselves. We're crushing. This is easy. And then you get to this one, and you guys will all get 4e. But the correct answer is 6e. So let's see if you can get 6e. Yeah, second derivative at 1 is the goal here. The second derivative at 1. Exactly. Everybody gets 4e. You're wrong. It's 6e. No, I'm right. No, sorry.
All right, can you show me personally?
Yeah, you're making the classic error. You forgot what to do if you have x's times x's. Way to go!
No, I got 4E.
Yeah, everybody gets 4e. Yeah, no, it's 6e. It's 6e. It's not 4e. All right. Put you guys out of your misery. Y'all did a good job with your first derivative. Good job. Good job. We get 2x e to the x squared. All right, great job. First derivative correct. But when you take the derivative of 2x e to the x squared, you have to recognize that it's x's times x's, which means for your second derivative, you need the product rule. The derivative of the first times the second plus the derivative of the second, we know what to do, we've done it, times the first. Plugging in 1, I get 2e plus 2e times 2. Well, that's 2e plus 4e, and that's how we get it, 6e. So don't forget about rules while you're doing derivatives of derivatives. Moving on. What? Now I got 4 e's and 2 e's. I add them together, I get 6 e's. Okay. What is the derivative of e to the f of x?
That's it. Yep. I'm on it.
Okay. You guys remember when we had stuff like, hey, h of x equals f of x, g of x? Remember these table problems where you had to take the derivative, but the derivative was very notational, but you had to remember your rules. And it's like, oh yeah, f prime g plus g prime f. Well, this is like the same idea. We have this notational derivative that we need to take. What I noticed is that it's e to a power, and the power is something other than x. So I'm going to put a set of parentheses in there, and I'm going to O and I it. I'm going to follow the rules, which are take our derivatives, and then what starts in the parentheses stays in the parentheses. The derivative of f is f prime. So g prime is f prime, I'm going to put that in front, times e to the f of x. Okay? This is your notational derivative of e to an f. Now I'm going to plug in 1. Sorry, negative 1. And now you guys are going to talk to your neighbors and tell them, shh, we got more stuff to do. Where can you get this information from this graph? Now, I'm told that the graph of f is shown, so the red line is the graph of f, and it's got a tangent line at x equals negative 1. There's the tangent line at x equals negative 1. Tell me what is f of negative 1 and what is f prime of negative 1? Go! Not negative. You have the right idea.
Oh, we can do like.
Or just rise over run. So,
Yeah.
Oh, it's that line? How do you know it's line?
well, it's told that this is the tangent line to f at negative 1. The graph of f is the tangent line at negative 1. So that's the tangent line, that's the graph of. Yep. So, you are correct. The slope of that tangent line is f prime, that's negative 5. The y value that they share is f. We get negative 5e squared. The slope of this line is negative 5. Down 5 over 1. The y coordinate of this line is the y value. Dot the y-intercept. Okay. We got to move on, but just showing you this, mostly for the video, that this is not a chain. This would be a product. We need to move on. So this would be the product rule with f of x times e to the x. This is not a chain. That's a product. Okay, but we got to move on because we got to review all of Unit 3. F prime times e to the x plus the derivative of e to the x times x. Yeah. parentheses around f of x, parentheses around e to the x. Okay, ready. Horizontal tangent, when a derivative equals 0. Cool. We took this derivative, so I'm just going to write it down for you. I know you might not remember that we did, but we did the derivative first times the second, plus the derivative of the second times the first. That's the derivative we got. We got this earlier. But we are now into the next step of what can we do with a derivative. Well, we can see what x values will produce specific slopes. We can solve equations. Now you see this equation and you're immediately intimidated. You're like, I got e's, looks crazy. But you will find a common pattern with all the rest of the questions we're about to do. It's a lot of product rules, and you will notice the e to the power will show up repeatedly. We have one term with an e to a power times 12. We have another term with e to the power times 12. Consistently, for the rest of the problems we're about to do, you're going to want to factor out the e to the power because you can. Makes things a lot easier to look at and to deal with. So I'm going to factor out not just the e to the power, but 12e to the power. What's left from the first guy is the negative and the sign. What's left from the second guy is the cosine. Okay, so at least this is easier to look at. But now we got to talk about, well, we have a product set equal to 0. We need to figure out when does this equal 0 and when does that equal 0. So when does the 12e to the negative x equal 0? We are not going to go through the examination, but I just want you to know e to any power, whether it's a negative power, a positive power, a 0, is always positive. E to the x is always positive. It grows really quickly and it goes towards 0. This is very important. So we just factored out an e to the power times 12. Well, this never equals 0. It's always going to be a positive because of the positive 12 and e to the power is always positive. I can essentially ignore it because it'll never equal 0 and it'll just be a positive value. I just have to pay attention to when negative sign plus cosine equals 0. We've solved this in the past. You had it on your test. Many different ways to get pi over 4 and 5 pi over 4. The question is, when does it first have a horizontal tangent? So I'll just pick pi over 4. He'll sign out and everything. So. Cool. Going to change this to x equals pi over 3. Going to ask a question, when is this function increasing or decreasing at pi over 3? Tell your neighbors, how do you know if a function is increasing or decreasing? Okay, now what's really important, guys, is don't do extra work when you don't have to. You're probably thinking, oh, we got to look at the signs of our derivative, a sign analysis. But honestly, you don't have to do so much. You guys were able to answer this question on all of the previous problems we did. Whenever you found a slope, if it was positive, you knew that the function was increasing. You had the translation. If it was negative, you knew the function was decreasing. Don't do a full-on sign analysis. Instead, just figure out if after plugging in pi over 3, you get a positive or a negative value. Now I'm going to write down the derivative, and you're going to tell me, what do we get after plugging in pi over 3? So I got cos x e to the negative x plus negative e to the negative x sine x. Tell me, after plugging in pi over 3, do we get a positive or a negative number? Go. try. If we forgot the cosine and the sine of pi over 3, I'm a little sad. I'm a little bit sad. I thought I taught you one way that will stick with you, where you're thinking 60-degree triangle, the tall 30, 60, 90 triangle, where the sine is the longer vertical side and the cosine's the shorter. Hopefully we get here, but then a lot of students are like, I have no idea whether this is positive or negative, but this is where the thing that I told you you will be doing every single time will help you. What did I tell you you're going to be doing every single time from here on out? Factor out the e to the power and know that it's a positive. E to the power can never be negative. E to the negative pi over 3, I just kind of forget about it, and all I care about is 1/2 minus root 3 over 2. This is a big fat positive. I know this is a longer side of a 30, 60, 90 triangle, so I know this is a bigger number. So 1/2 minus this has to be a negative. I don't know exactly what it's equal to numerically, but I know it's negative, which I know means the function is decreasing. You can factor them before with your x's and then plug in. Gets the same result. Cool. Now, that was just 1 point, but now we're going to ask you about intervals. What interval is this function decreasing? I bet you could do this if you tried. Go. Go. I did it too. Hey. X squared. X squared. You wrote it as x cubed.
Yeah, can you just do your head?
What?
Oh, wait.
X squared. So that's correct. That should be x squared. You got it. Keep going. Imagine that wasn't there. Would you know what to do with that? Of course you would.
Oh.
Yep. You got it, Ham. You're there. Imagine that wasn't there.
So what are we plugging in though?
No, I'm finding an interval. So what do? I need to do a full-on sign analysis. I need to find the zeros of that sign and then analyze the sign. So set this equal to 0. Yeah.
So
Just like we did last unit all the time. Take the derivative and set it equal to 0. But imagine that, which is weirding you out, isn't there, because it's just a positive. Could you solve 2x plus x squared equals 0? Yeah, I bet you could. I would say it's -2 to 0, but we're just talking semantics. No. You're right, but same thing. No, I think you're very much on the right track. All right, good. So, reminding us to find an interval when a function's decreasing. This is like your day 2 of unit 3. You take your derivative, you set it equal to 0. It's not something that's easily done if you look at it right here, but after factoring out the e to the x, and honestly forgetting about it because it's a positive, You're like, oh, when does 2x plus x squared equal 0? Hopefully many of you are like, oh, I could just factor out an x. Yes, you can. X times 2 plus x is the same as 2x plus x squared. Then, hopefully you said x equals 0 and negative 2, and those are your locations of your horizontal tangents. Your critical points, your possible maximum locations. Now you check your sign, and you see f is increasing, then decreasing, then increasing. F is decreasing between negative 2 and 0. Cool. Let's skip the next one, though it's a good one to do. You'll see it on your homework, and go to this one. Okay, ask for when the function is decreasing and concave up. Guess what? We'll have to do our first derivative sign analysis. We'll have to do our second derivative sign analysis. Is it a product rule or is it an outside-inside is a great question. What do you think, team?
Product.
It's not e to something other than x. It's just e to the x. So I'm thinking if it's something other than x, then chain rule. I'm thinking product rule, so product rule. Keep going. Yeah, you're good. We got the derivative of 2x plus 3 times e to the x plus the derivative of e to the x times 2x plus 3. I need to somehow set that equal to 0. Don't copy down. You should be able to do that. Now, I factor out an e to the x, and pay attention to what I get. I get a 2 plus 2x plus 3 is left over from the term on the right. Which means this is 2x plus 5. We set that equal to 0. There are no solutions from e to the x. E to the x is just positive. I just get negative 5/2. Cool. That's when 2x plus 5 equals 0. We can figure out that f is decreasing to the left of negative 5/2. Hooray. But now we need to answer about concavity. We don't get concavity unless we have our second derivative. Cood, I can't believe your phone is on that table. Yeah, it definitely is not meant to be on the table. That's right. You get negative 7/2 to negative 5/2. Negative 7/2 to negative 5/2 is the correct answer.
That's crazy. Why are you
Later. Thanks.
Can I come in on like next B-Day to like go over my test and then do like text like actually like do the test before my time after that?
Friday, Tuesday, sounds good.
When are you gonna retake? If I get it, and if I think I can handle it, can I go to the? So I'm gonna graduate almost really.
Sure, Andrew. See how it goes. Not till the second semester. Like, this is kind of one of those things where it's like, we're talking about it, hypothetically. We don't really get into it until you know more AB stuff.
Okay, then I'll see then whenever it gets closer.
You kind of have to make the decision sooner rather than later, unfortunately, with the way that AP signups are.
Then what do you think? I spent, like, the thing is, I spent a lot of Sundays studying for my test.
I know.
And then I got it.
I know.
It's like,
So that's why it's like,
but if there's no, like, I could still do good on the part, like, could I still get, like, a 4? Like, if I did really
you
bad
just do really well on the AB part.
Yeah.
You mean, and do poorly on the BC part, yeah.
So I'll talk about it.
Yeah. And what do you want to study next year?
I'm going to be a biology.
So you might need Calc 1, you might need Calc 1 and Calc 2. Maybe look at the schools you're applying to.
Okay. Thank you.
Yep.